Okay, Wiz. So here we're talking quantization again today. This is something that kind of sounds like the OG. We got GPTQ. That's kind of the whole thing, right? With quantization, we're quantizing these GPT models. Was this the original? Is that why they called it this? Or is that just a misnomer?
I mean, you know, is it the original quantization method? No. Is it one of the original quantization methods applied to generative pre-trained transformers? I mean, kind of, yes.
Yeah.
Certainly, it was one of the first ones adapted specifically for the architecture and the use cases of the architecture.
And therefore, it deserves a little time from us, deserves a little time from our audience. If you're going to be rooted in the fundamentals, the concepts and code that sort of came up in the game, this is an important one to look at, right?
Exactly. If we go through all of the ways we've done quantization, we leave this out. It's not talking about Gretzky when we talk about the history of hockey, right?
Classic. Okay, well, I'm pumped to dig into this today, and you're going to benchmark GPTQ versus AWQ, which we've already looked at, versus like a naive quantization. And we're going to see by the end of this thing how quantization works and which tool to pick out of our quantization tool belt when we're ready to build, ship, and share, right?
That's absolutely right. Absolutely.
All right, let's get after it. Thanks, Wiz. We'll see you back in a bit. Today, everybody, we're talking GPTQ. I'm Dr. Greg. That is the LLM wizard, aka the Whiz. We are AI Makerspace, and we're excited to talk more with you today about inference optimization and GPU optimization. We're going to do a bit of a deeper dive into quantization today to really just kind of pull out the core aspects you need to know when you're working with LLMs, give you some nice visualizations, and try to connect the pieces of the quantization puzzle that we continue to assemble, certainly for myself and hopefully for you guys as well. So strap in. Let's go ahead and jump into GPTQ today. Questions along the way. Any cues, throw them in the Slido, and we will upvote all of your favorites. Make sure that we answer everybody before we get done with the sesh today. Okay, GPTQ. What's really going on? Well, that's what we want to get a handle on today. We want to align ourselves to really the core fundamental aspects of quantization that allow us to see the difference between methods. This is one of the things that we're really going to have to kind of dive a little deeper into today. And then we're going to talk about how GPTQ kind of compares to and sort of served as a precursor for AWQ. And we're going to do some benchmarking and we'll show you how to use each one. And we'll answer the question like, should we be pulling a tool like GPTQ off the shelf today? If not, why not? And what should we be using in its place? So when we talk about quantization, there's a lot of ways to sort of dispense with the complexity, and maybe that's useful in some cases. Today, we're going to go a little bit deeper. And that's going to form the basis, taking what we know about AWQ for our ability to kind of understand and look further back towards GPTQ. And it's not just AWQ. There's also ideas like blockwise, K-bit quantization that we'll bring into the fold today as well. We want to stay rooted in the idea that when we're dealing with LLMs, they're very big. We have to run them on GPU so we can accelerate the inference or the training that we're doing with them. So all of the quantization techniques that we might look at are going to be within either a training or an inference paradigm. We're focused on inference because, well, most of us aren't training our own models. We're pulling them off the shelf. We're maybe messing with them a little bit, including quantizing, and then we're trying to ship them into an application that's going to get in the hands of real users. So this sort of general arena we find ourselves in. We might call it the post-training phase. We talked about this last week with RC, and there's a lot of things you can do in the post-training phase. We're talking about post-training quantization. When we're doing post-training quantization, we want the output from a single inference, from a single input that flows through the network, to be about the same as the output that was generated with all of the original weights. So if we quantize all the parameters, all the weights, we want the same kind of thing coming out. If we did that, well, then that means we kept performance high and we decreased cost. In other words, increased efficiency. Those are all good things that everybody wants. And it's important to understand that many weights are more important than others when we look inside of an LLM. In fact, the most common model weight in all LLMs is 0. Bunch of empty space in these bad boys. What's going on? Well, our task when we pull this off the shelf is to extract sort of all of the signal contributing weights in the right amount, in the right type, in the right form, so that we can get that good output. Because we don't always need super duper extra fine grained detail. Sometimes we just need the big picture. And this is more and more true as we can kind of specify the exact task that we're building our application to perform. And, so in general, we want to think about quantization as it's allowing us to sort of kind of not worry so much about the zeros out there, squash those, and then squish or compress the stuff that really does matter. And again, we don't care about most stuff. Okay, so we want to really focus in on the stuff that matters. And the stuff that matters is the original weights that are of sufficient size. So if we think about how quantization works, we showed this diagram last time. This is how it works, but does this quite make sense to you right now? Probably not if you're watching this event today. And so let's dig in a little bit deeper here into this idea of reducing precision through this binning or this blocking that we are doing, going from original weights, original parameters, down to quantized weights or quantized parameters. So digging in, the big idea is that we want to represent billions of values efficiently. Okay. Now, what is efficiently when it comes to our weights? Well, we can have more precision or we can have less precision when we're reporting what the number pi is. The same is true with every weight in an LLM. And, is 3.140625 even necessary? Maybe just 3 is fine. It depends on my application for pi. And pi is kind of chilling by itself, so it's not part of a huge network of other weights that all equally have importances. Those importances matter, and it's those importances that we're going to kind of continue to zoom in on as we investigate here. When we think about precision and we think about how we can represent numbers as floating point numbers or integers, the number of bits in this case, the integer 8, the signed int 8 has 8 bits. The number of bits tells us how wide the range of possible values that we can represent are. So in a full precision 32-bit representation, this is the kind of thing we download a model in, is full precision. Well, we can represent like, wow, 10 to the 38th numbers. That's a lot of numbers. Whereas in an int 8 range, we're only looking, between like, we're looking at 128 basically, right? Like we're not in this scale of the universe space. And remember, most model weights are close to 0. So one of the questions you might ask as we talk about precision and as we talk about most model weights being close to 0 is like, how much precision do we need around 0, right? Because can I just take all of the numbers that are even remotely close to 0 and just call them 0? Well, people are trying stuff like this. And it's working pretty well, actually. There's another piece that we need to bring in here, another key assumption, because it's kind of baked into this idea that most model weights are 0, but we haven't explicitly stated it. And that is that model weights are normally distributed. Now, that normal mean, right, you might sort of locate around 0, meaning the majority of the weights are around 0. Okay, so we're sort of aligned with what we're seeing. The assumption seems to align with the empirical evidence of large language models. And so we're kind of, all right, normal distribution, most model weights are 0. We want to figure out the precision that allows us to capture the relevant information around 0, but also around other numbers as well, right? And so this is where quantization starts to slot in. Now, there's one other piece that's going to help us understand GPTQ later, and that's this idea that 0 is quite important, and there's ways to make sure that our initial unquantized range is centered around the same spot as our quantized range. Showed here, we have the zeros all lined up. Beautiful. It sort of makes sense, right? It's sort of the simplest way we might do it. If we think of this idea of the simplest way we might do a quantization, one of the things that we would probably consider is that, well, what's the biggest possible parameter or weight? Let me just take that number. Let me take the absolute value of the maximum weight value. In this case, we're showing it as 10.8, let's say. Let's say that's the biggest weight. It could be positive, it could be negative. We're taking the absolute value. And we're just going to set the range so that the min and max are both 10.8. And we're going to quantize accordingly. Now, if we have same range on the left as on the right, we can do this symmetrical, stay at 0, very nice, easy quantization. So we see, the 10.8 becomes 127, right? And then the lowest other range, we don't go all the way down to minus 10.8, minus 7.9. This becomes now 64. Okay. And note here, we've got a nice 1, 2, 3 on the left, 1, 2, 3 on the right, the one at 0. There's like a nice sort of, yes, okay, this seems to feel right and make sense. Okay. Well, what are we doing here? We're just compressing information. This is a compression. This is a quantization. So there's a loss of information here when we decrease the precision, the bit precision of the way we represent those floating point numbers. So one question you might ask is, well, can we go back? And the answer is like, well, yeah, well, kind of. We can never go all the way back because we just compressed it. But we can kind of go back. This kind of going back, this is this idea of dequantization. And this dequantization of going back sort of up the precision scale, this is where this idea of a scaling factor or a quantization constant or quantization error comes into play. Because essentially what we do is we take, check this out, follow me, the average of the standard deviation of the errors in each bin. Okay, so wait, hold on. We're taking the average of the standard deviation of the errors in each quantized bin, in each quanta. Okay, this is visualized like this: the average of the standard deviation of the errors. So these two are going to be both in this bin, these two in this bin, and so on. Now, the bin has a center point, it has some range. And we're going to sort of say, okay, well, how far off is this point from the bin? How far off is this point from the bin? And I want a single number that allows me to sort of talk about just how far away all the points are from the bin that we put in there. And this is sort of the simplest way that you can imagine doing this. And you can obviously get much more complex from here. Now, we might also call these bins blocks. And in the LLM space, we have seen stuff like the 8-bit optimizers via blockwise quantization paper from Tim Detmers and others come out 2021. Okay, so this idea of blockwise or binwise quantization is not like super new. And it is kind of the place to start in your understanding. Now, every time you see a paper like this, it's not just that it's blockwise quantization. You'll always see like, well, fine print. And in this case, the other fancy stuff here is like, well, there's also dynamic quantization, which is like a nonlinear optimization for some of the quantization. And there's also like, we make sure that there's like a stable embedding layer so we can reduce gradient variance. And so there's always like these little mini optimizations that people are doing in addition to sort of the main point of any of these papers. So that's why it's nice to be able to go, pluck these off the shelf and just use them, because the authors generally worked very hard on this. Now, when we think about these quantization errors that allow us to go back, they're allowing us to do what we call dequantization. Again, some information is lost, but not all of the information is lost. So 5.47 after we quantize and dequantize might become 5.44 and so on. Is that good enough? Well, the answer is like generally, yeah, it's good enough. We can also cast this into a slightly different light and just sort of subtract the final dequantized from the original. That's what gives us quantization error. And this idea of quantization error is a place where we can start to thread together classic quantization into more advanced techniques like AWQ and GPTQ. So with all this in mind, let's recall AWQ that we covered last time. We said, okay, well, there's two steps. There's what's called weight-only quantization, and then there's the automatic, this magical reduction of quantization error. Quantization error, okay. And this weight-only quantization with the activation-aware weight quantization approach, AWQ, allows us to sort of protect the weights that are, quote, most important as identified by their activations. And part of this automatic reduction of errors is accomplished by what the authors call on-the-fly weight dequantization. So what's interesting is they kind of throw out like 99% of the weights here. So they keep 1% of the salient weights as determined by activation. And they're doing this on-the-fly weight dequantization that allows them to sort of get around this idea of doing mixed precision arithmetic. So it's pretty cool, and you should look closer into it if you're really into it. But again, it's not just weight-only quantization and automatic reduction of quantization errors. It's also like a bunch of other little things, including stuff like kernel fusion, including, specific layer normalization stuff, attention layer, stuff. And, I think, again, the details of the micro optimizations are cool, but often not quite the big takeaway or the point. So check that out if you're kind of more interested in that. Now, let's take a look at the abstract, knowing everything we know now, and see if we can really kind of grok AWQ. Okay, AWQ finds that not all weights in an LLM are equally important. Dope. Sounds good. We're on the same page. Protecting only 1% of salient weights can greatly reduce quantization error. Oh, okay. So if we only focus on the weights that matter the most from activation, then I'm not going to end up computing a bunch of additional quantization error, because I'm not going to be really computing it for the things that don't matter as much. Yeah, that makes sense too. To identify salient weight channels, we should refer to the activation distribution, not the weights. Check, check. So it could be a big weight number, low activation. Go ahead and ignore it. To avoid the hardware inefficient mixed precision quantization, we mathematically derive that scaling up the salient channels can reduce the quantization error. So we see this like intrinsic focus on reducing quantization error and doing it in a way that aligns with our assumptions and our knowledge about what's really important inside, which weights matter the most, which are the most important. Okay, so if we zoom in here again on AWQ, this paper is from June 2023. At the time, they said the closest work is GPTQ. That's the people who are the closest to what we're doing. They put something out, and that we got some inspiration from that. So here we are. GPTQ. What was the inspiration? GPTQ seems to need to connect blockwise k-bit quantization from 2021 to AWQ from 2023. What's really going on? Let's take a look directly at the paper first here. Again, GPTQ, epic name, feeling pretty OG. An epic start to this paper. GPT models, blah, blah, blah. Okay. Due to their massive size, even inference for large, highly accurate GPT models may require multiple performant GPUs. Got it. Same page. While there is emerging work on relieving this pressure via model compression, okay, I'm tracking. It's not there yet. In this paper, we address the challenge and propose GPTQ, a new one-shot weight quantization method based on approximate second-order information. Okay, one-shot weight quantization, second-order information. Our method more than doubles the compression gains relative to previously proposed one-shot quantization methods. Okay, one-shot doubles the compression gains. What does that mean? Let's dig a little bit deeper into the story of GPTQ. As they'll tell you in the paper, again, circa 2022, only basic variants of round to nearest quantization have been applied at the scale of GPT 175 billion, GPT-3, right, back in the day. So this includes the Detmer's paper. While this works well for low compression targets, like 8-bit weights, they fail to preserve accuracy at higher rates, higher compression rates. What does that mean? Well, it means even lower bits. In this paper, we're like, no. Yeah, 8-bit is cool, but what if we went to like 3 or 4-bit? That would be even cooler, wouldn't it? And turned out in this extreme quantization regime, and they were even messing around. They were like, can we go to 2-bit? You know? And then since then, of course, people are like, can we go to 1-bit? You know, it's like, well, sometimes, yeah. And so it's for this reason that this kind of was a bit of a landmark piece of work, right? They're sort of pushing the envelope here, which is great. That's what we want. And, you know, we see this today manifesting itself. This is a book that just came out from Jay Alomar and Martin Grutendorst. And the idea is GPTQ is quite well known. Great naming scheme, but it's quite well known for quantizing down very low, down to this 4-bit level, not necessarily to the 8-bit level that we saw in the Detmer's paper. That obviously has since, you know, we've quantized down a lot more, but this was kind of where this thing started. And today you're going to find compatibility for GPTQ sort of all over the place. Okay. And it'll be like, it won't necessarily be stated as such, right? But if it really brought 4-bit quantization onto the scene, we can kind of see echoes of it. When we look at inference and serving tools, things like Llama, or, you know, straight up, if you're going to be a gold standard inference and serving tool, you're going to want to make sure that you support quantization techniques that people are used to. GPTQ and AWQ are two of those. And these are more classic, more naive implementations. Okay, so all that said, let's talk about how GPTQ actually works. And this is where I'm going to give you some trailheads, okay? But you are going to have to dig into some of the math yourself if you want to really, really grok it. But we will show you exactly how to use it so you actually don't have to do that. One of the key things that differentiates GPTQ is this idea of layer-wise quantization. This means that each layer is processed independently sequentially. And this is something that adds a little bit of complexity because that's really not what we were doing in the naive implementation. We just said all the weights, quantize them. Now we're doing this layer-wise thing. And you could start to intuit, like, why would we want to do it layer-wise? Well, when we're in a layer and we start to lose dimensionality as I go to this next slide, but stick with me. We're in a layer. Well, stuff that's within a layer has some sort of intrinsic connection already. They're sort of related. And it's this relatedness that we're kind of capitalizing on eventually to ultimately reduce quantization error, right? Okay, so how is this kind of working exactly? Well, what we're doing is we're calculating a sensitivity, and we're doing that with what's called the inverse Hessian matrix. So if you haven't been in grad school for a long time like me, don't worry so much about the specific details of the matrix algebra here. Just know that we sort of take the layer, we take weights, and we calculate an inverse to this matrix, and we can look at the numbers. And if it's a low number, it's actually quite important. And so we want to pay attention to that. And this is what is meant by the second order information, because this inverse Hessian is a second order derivative of the model's loss function. And again, like, these details aren't super important. What's important is that we're trying to figure out how sensitive the model's outputs are to, get this, changes in weights. Changes in weights. So not two weights, that is a sort of important point, but changes in weights. So essentially, we're calculating the importance of each weight in the layer, the weight importance per layer. When we do this on a per layer basis, we can minimize the quantization error. One last final point that I encourage you guys to dig into if you're interested in going further on this. We are calculating this quantization error based on these importances that we calculate out. We're also doing something called 0-point quantization. And what we're doing here is, because we're not sort of taking all of the weights in one big set and quantizing them down, we actually need to sort of go layer by layer, and we end up in this space where we're not doing a symmetric quantization, but rather we're doing an asymmetric quantization. And the asymmetric quantization requires us to do a little bit more math to align our 0 points in a way that is going to feel kind of like the intuitive symmetrical piece we looked at before. And again, there's a little bit of math here to go and to align these 0 points. But in each layer, this is happening. So this is an additional piece of complexity that we need to mention. Now, of course, right? Layerwise quantization gives way to the inverse Hessian and the sensitivity. That's the importances. And well, actually, there's some details associated with 0 point asymmetry, but there's also other details because it's another paper and the authors always do interesting, cool optimization things. So, they added dampening factors to the Hessian matrix. They did what they called lazy batching, and they're pre-computing some information. And so again, there are these micro optimizations that, again, if you're into it, if you're into micro optimizations, jump on in, see what you can learn, see what you can understand. But our focus is always building, shipping, and sharing, rather than just trying to truly understand every single micro optimization. And it is to that end that we turn our attention for the day. Because what we want to do here is we want to approach inference with GPTQ in a systematic way. We want to take a look at, okay, we've got a basic model. We're pulling it off the shelf. This is a classic that we're going to essentially use in our applications that we build. What should we choose as a method for quantization? Should we choose GPTQ? And by the way, we're going to use the GPTQ model repository. It's not populating here, but you'll see it in a moment. And just like we chose auto AWQ last time, and this is going to allow us to compare naive to GPTQ to AWQ. Let's do some benchmarking. Let's see if we really get faster with GPTQ, or if maybe just the story was enough for the day. Whiz, walk us through benchmarking these things against one another, and we'll come back for a discussion of how to choose one over the other. Over to you, man.
Yes. Okay. So, this is as straightforward as it gets for the implementation side. Basically, all we need to do is we need to have some number of endpoints, and we want each of those endpoints to be a different, basically, quantization strategy. So you can see here we have our Llama 3.1 int4, our Llama 3.1 AWQ, and then our GPTQ implementation. So we use these three endpoints, which were all running Llama 3.1 Instruct, and we just hammered them with a bunch of requests, and we see which one is quote-unquote the best based on the speed. And the results will not shock you. They're exactly like what you'd expect. Okay, so basically, what is GPTQ doing? Greg talked about it quite a bit, but the idea is that it's quite straightforward in the code, right? So we have a pre-trained language model for each layer. And remember, layer here, great question from Blackcurrant in the chat, right? Layer is each sublayer of the transformer block. So if we have, say, a number of transformer blocks, those are each going to have their own layer, which is classic. We're also going to look at, quantizing those column by column using this Hessian matrix, as Greg talked about. And after each column, we update the remaining weights to compensate. This is kind of like the big idea. So whenever we do our quantization, we have some error, and so we need to update the remaining weights in order to reduce that error. And we just keep doing that iteratively, over and over again, over and over again, over and over again. The special tricks we use are we can quantize in a fixed order instead of a greedy order. We can process the weights in batches. Classic, batches let us do things in parallel. Parallel means we can do, 6 operations at the time it takes to do 1. And then we can use this Cholesky decomposition for numeric stable. It's just a fancy factoring method. There's nothing to it other than that. And then we have a compressed model. So what is the Hessian matrix? Well, as Greg told us, it's just a map that says what weights are most important. And instead of using activation, specific activation-aware quantization, we use fancy math to get there. That's the only difference. For the code, right? I mean, these are all just functions that we implement. So there's no real difference. One thing to keep in mind is that we actually can, this particular point, right, how we quantize, it is a hyperparameter. So we can choose to either do this in this greedy order, or we can do it in a fixed order. If we do it in the fixed order, then the results, the output model should be slightly less performant, but we can do it faster. Versus if we choose this greedy order where we say we quantize by the least important weights to the most important weights, then we can do it a little bit better. But it'll be slower to do. The actual process of quantization will be slower. So important to keep in mind. Okay, so first of all, we're going to need our Hugging Face tokens. So we're using Hugging Face inference endpoints, and then we're going to use our notebook login. To log in, we have just a bunch of strings. The strings don't matter at all. And we're going to test our inference speeds. We're going to care about the following metrics: time to first token, or TTFT, inter-token latency. That's how many, how long between each token as we generate it, and then tokens per second, which is a more understandable metric. The reason why we separate out TTFT and ITL is that the way that these endpoints optimize the inference is they actually there might be a little pre-fill stage, or there might be some additional latency to get to our first token, but then every token past that is going to be quite a bit quicker. And so we care to measure the time to first token because there is an expected lag or gap to the first token, and that would influence our average latency if we didn't consider that. So we just have this helper function that does all that. That's great. And then we're going to have our TGI endpoint that's pointing at bits and bytes. Pretty straightforward. it's pretty slow. It's not too slow, right? 12.09 tokens per second, 0.33, right? So not bad. We're around the threshold of human reading speed, which means that this is still producing outputs fast enough that we're not going to, most people aren't going to be able to outread the generation, which is nice, but it is still kind of slow. And I mean, almost a third exactly of a second for time to first token. You can feel that, right? Noticeable lag. So let's try AWQ. Again, we're just using these models from Hugging Quants on these endpoints that have gone through the AWQ and GPTQ methods. And all of them are in int4 or NF4 for our naive example. For this one, time to first token, much lower, and our inter-token latency drastically lower, with our tokens per second rocking up at 42. You're definitely not outreading this unless you're a speed reader, which most people aren't. But so we love to see these numbers. AWQ, it's fast. We knew it was fast. Let's see about GPTQ. Same thing, Hugging Quants. And you'll notice that we definitely have, so 28.58 is less than 42.92, but it's quite a bit bigger than 12, right? So it's kind of fitting comfortably in the middle here. You'll also notice that the inter-token latency of these two methods is actually the same. So we have the same inter-token latency, and then we have the time to first token, which is massively increased compared to our AWQ. So the actual, most of the speed savings in AWQ is the initial token. Once the tokens are ripping, though, we find that those methods are pretty similar. So that is it's an interesting point because it can help guide when we want to use these methods, one versus the other, and the kind of relative savings in terms of the actual generation once it's begun are extremely similar, which is cool. Good to know. So how do we actually create a GPTQ model? Well, of course, we use a helpful library. This time it's called GPTQ model, which is a maintained fork of AutoGPT. So AutoGPT is not very well maintained these days, but GPTQ model is. And we have a number of parameters. Again, when we do our quantization, we can choose our bits, we can choose our group size. So bits is our target bit width, and then group size is how many how many numbers are we going to have per scaling factor, right? So per quantization constant. So pretty cool stuff. We are going to go ahead and we are going to quantize new research's MetaLlama 3.1 AP Instruct using this package. We'll add some logging because logging is cool. And then we're going to use the same data that we use to spam all those tokens to help calibrate. Now, this is something that is unique to GPTQ, which is we can have this calibration data set, which measures perplexity as we make changes, and that perplexity helps inform us as to how well our model is retaining its ability, which is very good. So it can ground us and help when we create those approximations of those Hessian matrices and we're computing things like loss. It can help us stay calibrated, which is very nice. You can see that we go all through all of the layers in all of the modules, right? So it's a lot. Hopefully all that scrolling indicated it was a lot. You'll also see that we have a number of layers, right, that are in each of these 31 blocks. So the idea is that we have our out projection, our Q and K and V projection, all part of our the zeroth transformer block. Same with up proj. We have our down proj, and then we repeat that for each of the 31 blocks in the transformer architecture. When we're finally done, which takes a little while, but not too long, to be honest with you, it was about a total of 13 minutes, as you can see in this cell. We have finally an output model, which was pre-quantized size of 30 GB, quantized model size of 5 GB, which is a 82.15% reduction, which we love to see. And then we can load it up and we can do generation with it, and that's always a good time. But you'll notice that like this is a massive reduction, right? So from 30 gigs to under 6 gigs is huge, and it's though it does take 13 minutes, right? This was done on a Colab instance. It only used 6.9 gigabytes of GPU RAM in order to both do this process and quantize or do inference on that resultant model. As well, we only used about 11 gigabytes of just traditional RAM for 13 minutes on an 8 billion parameter model to get that size reduction. I mean, this is quite fast. And one of the things about this GPTQ optimization versus the AWQ optimization is that it can be more flexible with architectures. So usually they're supported more quickly, as well as the support is more widespread. Though we'll talk about that a little bit, I'm sure, in the next few minutes. Before I go back to Greg, I'll of course remind you to subscribe, ring the bell. We're live every Wednesday. We love doing this. We love seeing you guys here. So there you go. Thanks for that, and we'll go back to Greg. You're muted, Greg.
All right. Yeah, thanks, Wiz. So we are going to go ahead and wrap with some conclusions. If you guys have questions, please throw them into the chat and we will get to them. And, you know, today we kind of revisited quantization. We kind of revisited this idea that we want to always be improving the performance, especially the efficiency of our models as we're ready to do inference on them, as we're ready to build things like RAG applications and things like agentic applications that really are going to be useful in industry today. We're typically focused on that inference paradigm, less the training paradigm. And when we're doing that, we're kind of talking about, we're talking about optimizing inference through quantization. We're talking about reducing the errors, number one, that come from quantization, but doing so in a smart way. So if we can sort of decide all of these things we don't need to pay attention to and then quantize, that's much smarter than, you know, simply trying to minimize quantization errors from the jump. We saw that generative pre-trained quantization, generative pre-trained transformer quantization, GPTQ, it kind of played an integral role at a moment in time and sort of paved the pathway for what would come next. It was looking at sensitivity to changes in model weights through that inverse Hessian matrix. That was the indicator of importance of the weights within each layer. Because we're going layer-wise with quantization, it does take a little bit longer, but there's also some additional flexibility because as we go layer by layer, it's like, well, if you go layer by layer, you have sort of a more expandable method to go to many different types of architectures with many different types of layers, right? So you can sort of set it to work on many different types of architectures, and maybe that's a place to think about using it today. In contrast, we have the Activation-aware Weight Quantization, AWQ, that is more and more of a best practice tool that you might pick up, where the activations are the indicator of importance, not the sensitivity calculation. And in that method, we're actually leaving the most important parameters in high precision while quantizing the rest into that lower precision. So if you have questions, please do share them in the Slido and upvote your favorites. But Wiz, I'd like to bring you back and start with a little important question first, which is which method should we actually use? Like, should we use GPTQ? Should we use AWQ? Should we have them both? Which one should we have close at hand?
Yeah, I mean, the easy answer to this question is use AWQ if you can. If not, use GPTQ. There is potential total memory savings that you could, draw lines across. And at the end of the day, for most use cases, these are going to be very similar. But yeah, I mean, if I'm just to say which to use as a default, I'm going to say if available AWQ.
All right, if available, AWQ. And then, I think one of the things, we started talking about this last time, but when we talk about alternatives to these things, like it seems like at any given moment in time, there's sort of like a baseline. This is a best practice. So I would recommend this. And maybe that's AWQ here. But as you look further into it, you see, okay, well, there's specific edge cases like, if something that's not a transformer comes out and we want to quantize it, maybe GPTQ is going to get adapted and that's going to be a slightly better thing. We're seeing sort of if we look at a technique like GGUF, which we didn't talk about today, but we also have these techniques that come in and they say, well, if you have much, much less compute, sometimes these things can be more useful. So, Llama versus Llama CPP is another example there. And so, I think like it does depend, but rather than just say it depends, it's like we like to have an answer. And so I guess AWQ is the answer. GPTQ, when am I pulling it out exactly? When do I want to use this thing? Or is it really just sort of a thing that we study and give credence to times past?
You want to use it if you can't use AWQ. And I know that sounds, like potentially not ideal, but the reality is that does happen. I mean, there are due to the long-standing nature of GPTQ, it is the most supported of these quantization methods because it's just been around the longest. So you're going to find situations where your model is supported by GPTQ but not by WQ, and there's no easy path to get an AWQ model. The other thing is that, again, GPTQ is flexible. As new architectures come out, GPTQ is going to be the kind of best first day quantization. And then something about like GGUF, right? GGUF is basically just a file format. You want to use it in situations where you're using something like Llama CPP, which is relies on that file format for fast and efficient loading and unloading of model weights into memory.
Yeah.
But otherwise, we're going to stick to our AWQ GPTQ if we have a GPU.
Okay. So yeah, and as we sort of continue this series, let us know if you're sort of interested in learning more about these other tools that we mentioned. We can certainly deep dive each and every one of them. So speaking of one versus the other, can you use both? Would you want to do that? Is that dumb?
I wouldn't say dumb, but they're doing the same thing, and they both prune the weights, and they both make they leave the model in a state that is non-compatible with each method. So combining them might be technically possible, but I can't see a situation where it would be particularly favorable.
Incompatico. Yeah. Okay. All right. So probably not. But try it out. Maybe you get a paper out of it. What is I'm gonna skip the next question. I'll answer it if we have time, just because this event wasn't on AWQ specifically. What kind of noticeable influence does quantization error have in the final output? So if I have slightly higher quantization error, am I really going to get a different generation?
Yes. The idea of both AWQ and GPTQ is that we minimize that impact. So what that means is that we are using these strategies because they minimize that impact, right? So like naive quantization, for instance, is just like everything's 4-bit now, right? Or in NF4 format, right? It's not caring about the the quality versus something like GPTQ, which is actively monitoring the change in perplexity, which is, while it's not a great metric overall, it does mean it's very, very good at saying the model is generating the same stuff that it did on this stuff before, right? We can measure, perplexity is very good at measuring that. So, this is the idea, is these activation-aware quantization strategies, which is AWQ and then GPTQ, both take into account the model's performance. And I think that is what makes them de facto better than naive quantization, even not considering at all the optimization for inference. So to answer the question, it does have a noticeable impact. Both of these strategies aim to reduce the impact as much as is possible.
Yeah, I mean, it's a question of like, what's your threshold of noticeable too, right? I mean, because we have this importance indicator inside that we're sort of tracking and measuring. We're saying that that's going to correlate to, differences that manifest themselves on a token basis in the final output. And maybe that's true for a specific amount of, quantization, and maybe there's quantization ranges that don't affect the token level in the end. But I think this is kind of what we have to play with, right? As AI engineers, is like, how much quantization can you get away with? You should probably go get away with that much, because
as much as is tolerable on your downstream benchmarks for quantization.
Yeah. I mean, because it's like, how are we leveraging our compute? Can we do it more efficiently while maintaining the same ish performance? It's like, that's what we're always asking. Okay. Why is dequantization faster than actual FP16 straight up multiplication? So why would I quantize and dequantize? It seems like I'm adding an extra step. It seems like maybe if I just straight up did inference in FP16, it would actually be faster. What am I missing in terms of orders of magnitude here?
It's a good question, because the answer is glib but correct. We do it because the thing that's slow is shuffling around these big old matrices with big old numbers, and also we can write very efficient kernels for things like dequantization. So famously, when Tim Detmers released Bits and Bytes, it was very slow because there was no kernel support. And then he added kernel support, and it was much better, right? So this is the same idea with dequantization. The savings we get when it comes to inference is that we are moving smaller amounts of information around, and then we can do that blow up and shrink down in the compute as opposed to shuffling it around memory. And that's essentially why it's going to be much faster for inference.
That's right. The old shuffling around in memory is where we want to not be.
We hate that. We hate that.
Yeah.
And the other thing too is, like, think of it this way: if I have a pipe that can hold 15 liters of water at a time, and we say each request is 15 liters, then my pipe can support one request. Now, what if we say each request is 1 liters? Suddenly, my pipe can hold 15 requests. And then think about the downstream impact of that, right? How many more requests we can process per unit time. And that is the idea of why we care so deeply about things like this reduction in memory. Because not only can we do the compute faster, but we can also do more of it at the same time.
That's right. Otherwise, you need more GPUs.
That's right.
More money. Yeah.
That's right.
And it's harder to make it back.
You need 15 as many GPUs. That's insane, right? So.
Okay, thanks, Whiz, for your insights today and for benchmarking GPTQ. We look forward to seeing you back next week for the next event. Guys, that's a wrap for today. Thanks for joining us to talk inference and GPU optimization with GPTQ. Hope you learned something today. about GPTQ, KBit, blockwise quantization, AWQ. Hopefully it's starting to come together for you guys. If you want to see more on inference and GPU optimization, let us know what you'd like to see. We'd love to get your feedback. And if you want to go deeper on this kind of thing and you're not in our Discord yet, definitely jump in. We'd love to see you start building, shipping, and sharing with all the legends in the community today. And if you want to accelerate your understanding of GPU acceleration and the underlying architecture specifically that we're capitalizing on in order to do these types of accelerations, the transformer architecture, check out our upcoming course on LLM engineering. Really grokking what happens inside LLMs is super useful when it comes to speeding up inference or training. That's the deep dive of the course we're going to close out the year with. So check that out if you're interested. Let us know if you have any questions, comments, or curriculum concerns. And that is all we've got for you today, everybody. If you're in San Francisco this week, check out the Llama Index Rag-a-thon. We will be live in person, our whole team. Dr. Greg, the Whiz, Sriracha, and Lusk will all be live in San Francisco this week. We'd love to see you there and start building, shipping, and sharing with Llama Index live with us. But if you can't come, stay exactly where you are. Keep building, shipping, and sharing exactly the way you have been, and share it with us. Tag at AI Makerspace on Discord, on LinkedIn, on Twitter. We'll help you amplify, and we'll hopefully help you get where you're trying to go. Until next week, everybody, keep building, shipping, and sharing. We'll do the same. Dr. Greg and the Whiz out. See you next time, guys. Bye, everybody.